This is Module 2, Arithmetic to Algebra, part of a professional learning series for Foundations of Algebra teachers. We encourage you to follow along and construct the visual representations discussed within this session. Feel free to pause at any time to share your thoughts, ideas, and questions with your colleagues. This professional learning series is designed to explore the foundations of algebra content and strategies for teaching that content by looking at the big ideas within this module. The first of the 4 big ideas in this module is that algebra is useful in that it helps us make sense of the patterns in our world. This big idea involves 2 things that all math teachers should strive to engage their students in every day. The first of these are the standards for mathematical practice. These 8 practices are a guide as to how we should be teaching the content of any math course we teach. Students engaging in these practices on a daily basis must see mathematics as useful, not because we say it is, but because they are using it to make sense. The second is context. Contextual problems provide students at all levels a place to start. Contexts in mathematics provide the opportunity for students to think and practice becoming better thinkers. Context may involve words or just pictures or videos. Look at the patterns in Sierpinski's triangle or the conch shell. Contexts for mathematical learning are all around us every day. We just have to present them to our students. What do you wonder when you see this picture? Problem-based tasks like this one and 3-act tasks like this one can also provide context for learning. Contextual problems and engaging students in the 8 mathematical practices get students interested in mathematics, which leads them to appreciating it as useful and worthy. The next big idea has to do with the symbols of mathematics. 2 of the most misunderstood are the equal sign, as well as the inequality symbols, and variables. In order to be successful, students need to be given multiple opportunities to build understandings of these 2 ideas conceptually. To build conceptual understanding of the equal sign while building other algebraic understandings, provide a context such as balance. Press pause and take a minute to jot down what you notice and wonder about the scales. Share with your colleagues and press play when ready. Much of what you notice and wonder will be noticed and wondered by your students as well. Wonders from students will likely be, which one weighs the most, or which one weighs the least? Once you have one or both of these questions, ask them to work together to figure it out. The discussions that come from these simple contexts will likely be some of the richest. Follow up with other equivalence ideas such as these. And others that can be found online at illuminations.com and Solve Me. Another idea for engaging students in conceptually understanding variables and constants is through number tricks. Try this one with me now. Think of a number, add 3 to it, double your total, subtract 4, divide the result by 2, and subtract the number you first thought of. Your answer is 1. Now take a look at one model and see if the representations help you understand this trick on another level. Finally, take a look at what picture representations can do to develop students' understandings of not only variables, but also what it means to undo the steps of one of these number tricks. These picture representations help build early understandings of some of the steps that we often use to solve equations but on a conceptual level. And to think, it all started with a little number trick. Number tricks like these can be found in Module 2. One of these tricks is a mathic prediction, which builds nicely off of a number trick like the one we just saw. What's nice about this task is that it uses one of my favorite manipulatives, sticky notes. Using sticky notes instead of bags is nice because they're cheap, easier to sketch, and any number can be written easily on a sticky note. Consecutive number sums and triangle mystery were both created using Scratch, a free online coding program. Students can take a look inside each of these and manipulate the code to create their own number tricks. They can then build one of their own from scratch. The third big idea deals with generalizing our computational structures. Most of the content in this module falls within this big idea. True or false sentences. Take a look at these sentences. Which are true and which are false? Press pause and engage in this activity. Be sure to provide reasons for your choices. As mentioned earlier, the meaning of the equal sign needs strong understanding from the conceptual level. True-false explorations help clarify this meaning, and that's really just one of the outcomes. It's important to engage students in the 8 mathematical practices, so listen to students' reasoning for their choices. Also, for false statements, ask students to rewrite the statement with inequality symbols to make the statement true. This provides students with more opportunities to reason about quantity, make sense of the equal sign. Allowing students to share their thoughts gets them out of their own heads and gets them talking like mathematicians. And with enough practice, they begin thinking like mathematicians. After students have some experience with true-false sentences, introduce them to open sentences, such as those shown here. Again, press pause and share your reasoning about how you figured out the number for each box. You may be surprised at what you hear from your colleagues. After using open boxes, try similar problems, replacing the boxes with variables. Relational thinking is what happens when students observe and use numeric relationships between two sides of the equal sign rather than actually computing the amounts on each side. For example, take a look at the first true-false sentence. Thinking relationally, I can tell that this is true because the start numbers 6 and 74 hundredths and 6 and 64 hundredths are 1/10 apart. And the end numbers, 3 and 89 hundredths and 3 and 79 hundredths, are also 1/10 apart. So the distance between the points on the number line didn't change, so they must be equal. Likewise with these open sentences. Take a moment to discuss these with your colleagues. How would you find the value of the box without computing? How well do you think relationally? Tasks like these empower students. Once introduced, these can be given to students on a consistent basis as part of a classroom routine. Exponents used to be one of my least favorite topics to teach because they led to scientific notation, and I really didn't like teaching that. Recently, though, I had a chance to hear how another teacher dealt with the same issue. Instead of giving students exponents rules to memorize, he thought about all of the mistakes students made, created a worksheet with all of these mistakes on it, and told them all up front that all of the statements were incorrect. The student's task was to identify the mistake, correct it, and then justify the reasoning. Students had 3 to 5 minutes of individual work time and then shared ideas with their group. This was all followed by a classroom discussion. Andrew Stedell is that teacher, and he wrote about this on his blog. In this post, he explains in more detail what happened and provides 2 more days' worth of this type of exploration. His post can be found at the links below. Square and cube roots can seem daunting and even tedious, especially if students are asked to memorize a list of them. But they don't have to be. Students can be engaged in the 8 mathematical practices while engaging in a contextual problem such as this. To begin, ask as before, what do you notice? Then write down everything they say. Pause here and take a minute now to do this with your colleagues. Jot down your notices. What do you see? Did you notice the multiplication table? Did you notice that the colors form a backward L? The squares are on the diagonal? These are all things students notice and more. But where is the square root? Do you notice that the square is near the center and all the other pieces of the same color are just as long as the side of the square? That's the root. The side of the square is the root of the square, or the square root. So, what about cube roots? If you ask students what they wonder about this picture, and you really should, someone will say something like, "Why are they colored that way?" If you don't have some cubes handy, get some, and look at the color groups. What do you notice? You're not going to believe it when you see it. The Pythagorean theorem is one of the most important mathematical relationships and demands in-depth conceptual investigation. One possible way to begin this investigation might be to assign pairs of students a different right triangle by specifying the lengths of the 2 legs. Have students draw their right triangle on grid paper. Next, students are to draw squares on each leg and on the hypotenuse. To construct the square on the hypotenuse, students can think of the hypotenuse as a diagonal of a rectangle. Then, through rotations, they can draw 3 more congruent rectangles that form a large square. By connecting the diagonals of these rectangles, they create a square whose sides are congruent to the hypotenuse. Students are to collect data from their classmates and create a table of data, including the area of the square on leg A, the area of the square on leg B, and the area of the square on the hypotenuse. The task is to look for a relationship between the squares. The last of the big ideas for this module involves recognizing, extending, and generalizing patterns. Take a look at this growing pattern. What do you notice? Though this may be a simple growth pattern, it may be useful to dig a little deeper into how it grows, allowing students to experience multiple ideas. For example, when asked to change the color of the sticky notes that seem to stay the same in this growth pattern, students may share one of these ideas. Note that the 2 underlined in red are similar. Build a table with students asking them what data they can collect. You'll get something like this on the right. Note that the columns are labeled stays the same, and changes. These are names that students usually come up with due to the question asked earlier. If one color represents those that stay the same, the other color must be a color that represents changes. Once a table like this is filled into stage 5 or 6, ask students what they notice. After they share all of the patterns they see, skip a few stages to facilitate the development of an explicit rule for this pattern. Then skip a few more. Finally, place a sticky note under the stage column. Ask students if they could figure out how many sticky notes it would take for any stage number you write on that post-it. Work your way through the table for the sticky note. The changes column for this example would be sticky note +1. Finally, remember the picture representations, though they're not included in this example from Module 2, Frameworks. Pictures also show a record of student thinking that they can easily return to, as you can see in this student work example. Many other free patterns to use can be found here at visualpatterns.org. To put all of this together requires 3 ideas. The first is differentiation. CRA, or concrete representational abstract, means that we're allowing students to build their own understanding. But they have to use all 3, concrete, representational, and abstract, from the very beginning. Just like in the growth patterns from earlier, students use manipulatives such as sticky notes or tiles. A sketch was included the first time and for many times after. And then there was also an expression at the end. So all levels, concrete, representational, and abstract, were seen from the very beginning. Here are some tiered tasks for working with growth patterns. Students can all work on the same standard and write equivalent algebraic expressions using 3 different growth patterns. The third idea is small group instruction. Meeting with small groups of students is certainly beneficial. It can be overwhelming to schedule sometimes. The 2 slides that follow offer some suggestions about how to manage small groups so as to maximize student learning. This is one suggestion that comes from the Social Emotional Learning and Mathematics session from Global Math Department. It lists a class size of 30 students to demonstrate you do not have to have a small class size to implement small group instruction. The GADOE is not suggesting the Foundations of Algebra class sizes should be increased to 30 students. This is another suggestion that comes from the Social Emotional Learning and Mathematics session from Global Math Department. It lists a class size of 30 students to demonstrate that you do not have to have a small class size to implement small group instruction. The GADOE is not suggesting that the Foundations of Algebra class sizes should be increased to 30 students. Let's keep the conversation going. The DOE has created a wiki space for high school teachers to engage in discussions about math teaching using the Georgia Standards of Excellence. Here, you'll find a forum to keep the conversation going and resources. And who knows, you might even make a few friends. It's a call to action, and you're invited to make a difference. Access this online community here. Speaking of online communities, if you're on Twitter, join the MTBOS. That's the Math Twitter blogosphere, where everyone has a voice and we all learn from each other. There are no dues and no applications. If you're a math teacher and you're on Twitter, you're in. If you're not on Twitter, this is your reason to join. If you're not a math teacher, why not become one?